So welcome back. So am I allowed to start? Okay, welcome back. So I just wanted to recap what we said last time. So last time we said that there's a solution to the strong field problem, which is the QCD axiom, and this is described by this Lagrangian here. So basically, I have a new scalar particle with an introduction to gluon of the kind A over the phi G tilde, no? And then there's also, in principle, non-derivative, derivative interactions with standard model. So here there's also some d mu A over 2FA, some quirks, Qi, gamma mu, gamma phi, Q, some coefficients. And then, so for us, it's important that so this coupling with the gluons will give an effective potential to the axion that is minimized at A equal to 0, and therefore this solves the strong field problem dynamically. And then we also saw that there is a coupling to photons that have two contributions. One that is model independent because it comes from the coupling to gluons at low energy. Okay, this basically comes with a mixing with the pion. And then there is another contribution that is model dependent. Okay, I told you yesterday that this E depends on the basically the charge of the quarks that are charged, the electromagnetic charge of the quarks that are charged under Petri queen. Okay, I wrote some formula yesterday for this E. But importantly, basically, only if you have a cancellation between the two, you can put to zero the coupling to photons. Okay, so this is just, and then I was telling you that a finite temperature, the mass of the QCD axion depends in this, it goes to 0, like temperature to the minus alpha, at temperatures much larger than the critical temperature of the QCD crossover, which is 150 MeV. Okay, and then we will use this formula with basically MA squared proportional to T to minus alpha, okay, for temperature larger than this. As you see, the important cosmological evolution of the axion will occur at temperatures that are above the GV. Okay, so we are in the regime where this is valid. Okay. Okay, even if it's not completely correct, but at least the last simulation that show this is valid. And then I finished by saying that we have a period of inflation, initial period of inflation, where the axion and all the fields that are basically lighter than the Hubble parameter during inflation get stretched over cosmological distances. In particular, also the axion. So for us, it is a good approximation to assume that the axion is constant, is homogeneous over our observable universe, and acquires an initial value A0 that I parameterize like A0 equal to theta 0 times FA. Okay, theta 0 is between minus pi and pi. Okay, just because the axion is a periodic potential. What I didn't say last time is that I will heavily use conservation of entropy density, which probably you have already seen last time with Francesco Delamo. Basically, the fact that the entropy is conserved, so entropy density. So basically, the entropy density, which is defined to be some factor that I'm not going to track, times the effective number of degrees of freedom in entropy, which also I'm not going to track, times the temperature cube. This is conserved comovingly. In particular, so this is equal to 1 over scale factor cube. So for me, I will use this conservation of entropy density. Basically, I will use many times that T times R times this G is equal to constant. Okay, and many times I actually will forget about G, and I will just write that T is proportional to 1 over scale factor R. Okay, this comes from conservation of entropy density, and you probably already seen this stuff last time. And the last thing I will use, well, maybe I will not use too much in these lectures, but it's good to know, is that inflation, in fact, doesn't really only lead to a homogeneous field. It actually also imprints small perturbations on the fields. Particularly, it leads to imprints perturbations on the inflaton and also all the light fields during inflation, which are, for instance, the axion. And so the perturbation on the inflaton, to the inflaton, also known as adiabatic perturbations, are those that imprint the initial density perturbations of the metric that we see. Okay, these are adiabatic because they're imprinted basically on the metric and therefore on all sources of energy, and basically it's adiabatic in the sense that they are both in the radiation, in the matter, and in principle all the forms of energy that couple to gravity. And this we sort of measured. We know more or less what they are, and we measure via the temperature fluctuations on the CMB. On top of those, inflation also imprints perturbations to the axion that are called is a curvature, because being the axion, since the axion is light, they get also this additional perturbation. So you can think that at the end, there are, on top of this homogeneous value, there's also some small perturbations, and these are of the order of hi. So this delta A are of the order of hi over 2 pi, hi being the above scheduled inflation. Okay, of course, if hi is very large, then these fluctuations are large. So while the adiabatic perturbations we measure, so the famous perturbations of delta rho over rho over the 10 to minus 5, these are the adiabatic. This one we measure. These ones instead are constrained, and we will see that we will use these are called isocurvature. Okay, isocurvature. This one are constrained, and this one will give some bounds on the models, basically bounds on the Hubble scheduling inflation. Okay, just to say, okay, this is standard stuff. So inflation imprints also perturbations on top of having a homogeneous field, and this is basically because of the fact that you can think of inflation as having a universe in a box with a certain volume given by the Hubble scale, and while the universe expands, basically the quantum fluctuations inside the box get frozen out as the universe expands exponentially. Okay, that's and the other order of hi over hi, because basically of the uncertainty principle in your box. Okay. So now let me. So and I finished last time by saying that in principle I should write the equations of motion of the axion in the universe, no, in the radiation domination just after the inflation, and they look like okay. They look like, well, I don't have to, okay, they look something like this. So A dot plus 3 HA dot, and then I have minus Laplacian of A over R square, and then I have in principle plus V prime of A to 0. So this is my other parameter, this is the axion, and V prime, okay, V prime of A, this is in principle a sign, but I approximate like MA square times A, because for now I'm assuming that the initial condition is close to the minimum. Okay, so I assume that this is V, this is A, and assume that A0 is close to the minimum. Okay. So that this V prime is approximated in this way. And also I told you that the gradients of A over R go to 0 because of inflation, and also A dot goes to 0 due to inflation. So in the end, I need to solve this equation without this term. Okay. So and with initial condition given by A dot equal to 0 and A0 equal, okay, A of a certain time t0 equal to 0, equal to A0, fixed basically by the choice of our multiverse, no? Depends on where we are in the multiverse, which is in principle uncalculable. So A dot 0, because the inflation also decreases the velocity. So, well, this at time t equal to 0. T0, yeah. No, okay, T0 with the initial time just after the inflation, if you want. This is just the initial time after inflation. Not now. Now is completely different. Okay, so What's the solution of this equation? Well, the solution of this equation is simple. So first of all, let me notice that both h depend on time, and also ma depend on time, because of the thing there, no? Because temperature depends on time depends on temperature, and in particular, if you do the calculation properly, you see that okay, ma goes like t to the alpha over 4. Okay, so let me show these two quantities. So h, I told you, decreases with time. So I'm showing here as function of time. I'm showing h. H decreases. So we are after inflation, we are sort of in radiation domination, we think, after a brief period of matter domination, maybe. So h goes like is equal to 1 over 2t. Last time I told you this. So this would be the Hubble parameter. And then the axion mass, okay, it depends if you're thinking about the UCD axion or an axion-like particle. If you are the UCD axion, it goes in this way. If you're axion-like particle, you have alpha equal to 0, so it's constant. So I'm taking the generic case of alpha non-zero. So I'm putting this MA that increases with time. So what happens? So there is a critical time that is important for us. I call T star. T star. That is the time when the Hubble parameter equals the axion mass. So what happens before or after T star? If you see this equation, what do you think happens? Nobody. So before T star, this term is negligible compared to this one, okay? Because the mass is much smaller than Hubble parameter. So for approximation, I can neglect this term, and the equation is a dot dot plus 3h a dot equal to 0, and the solution is famously a dot with initial conditions. So let me do here a t much smaller than T star, corresponding to Hubble much larger than H star. So let me also call corresponding Hubble H star, and corresponding temperature of the universe T star with big T. So at this time, this term is negligible. So the solution is A of T equal to more or less A0. So showing in a plot, like draw here, showing in this plot, I can just show the same plot, but with A of t. So initially, it's basically stuck at its initial value. This is T star, and here's T. Then what happens? Well, then at some point, the axion mass starts becoming larger than Hubble. And the equation now is obviously the same, but now it's the last term that dominates over the others. And this equation looks like that of a under damped harmonic oscillator. No, with a friction term, no, that decreases in time. So in this other regime, when T is much larger than T star, I have Hubble much smaller than H star. Okay, and this is under damp okay, harmonic oscillator with a frequency that decreases in time. So to find a solution, in principle, it would be very, very easy if h would be 0 and ma is constant. Okay, and for me, so to find a solution, what do I do? Well, I do this trick. So in this regime, I do the trick of writing phi instead of a. So I write a in this way. I substitute, instead of using a of t, I use phi of t defined in this way. Okay, I just factor out a factor of 2/3 of R to the 3 halves. Okay, then you have to take this stuff and put it in that equation. If you do that, that equation looks like something like phi dot dot plus ma squared of t. Okay, no, also let me do, for simplicity, the case where ma is not dependent on time, so alpha equal to 0. Okay, so for simplicity, let me do this. So this equation looks like ma squared, okay, plus, okay, minus 9 over 4 h squared, okay, minus 3 halves h dot phi equal to 0. So what I did, I just took this stuff, I plugged it there, and write the equation in terms of phi. So now the crucial observation is the fact that yeah, I mean, it's so maybe it's no good notation. Maybe I should write phi like this, but okay, this phi. Okay, long story short, the idea is that when Hubble is much smaller than the mass, then these two terms are much smaller than this one, no? Because okay, here I am in this regime where the Hubble is much smaller than the mass. This stuff goes like 1 over t square. This stuff also goes like 1 over t square, which is basically Hubble square. Okay, because h dot is also proportional to 1 over t. 1 over t square. Okay, and in the end, as you see, in this regime, I can neglect these two, and if phi really solves a proper oscillator equation. So phi solution, phi of t is equal to some phi of t star, okay, more or less, let's say phi of t star, times the cosine of ma times t. Okay, this is the solution. Which means that the solution for A would be A of t star, and I have something like a cosine. Okay, then I have some R of t star divided by R of t to the 3 halves, and then the same cosine of ma times t. Okay, this will be a solution for. So, all this to say that by doing substitution, you can easily see that this is the solution. So, what does it mean in terms of the field? Well, the field, yes. Because I assume that for simplicity, but then I will tell you what happens for when it's not time dependent. So it means that in the large time limit where t is much larger than this critical time where the two cross, then the solution looks instead more like a cosine. So the field starts oscillating with a period given by 1 over m. Okay, 1 over ma. And importantly, you see that these oscillations don't have a constant amplitude, but they have an amplitude that decreases with 1 over scale factor to the 3 halves. Okay. Okay. This is a fact that you can just obtain by solving the equations of motion in that way. So in terms of a picture, like you can think of okay, you have the axiom with a certain potential that is approximately like a quadratic. No, for the quadratic potential is a of a v of a as function of a. Initially stuck, the field is stuck at this point is 0, and this corresponds to this. And then at some point it starts oscillating with an amplitude that decreases in time in this way. Okay, this is the picture. So what is the energy density of the field during these times? So the energy density is the component 0, 0 of the energy momentum tensor, and the component 0, 0. I'm not going to derive it for you, but is the kinetic energy plus the gradient energy plus the potential energy. And the energy density is given by, okay, 1/2 a dot square plus 1/2 gradient of a modulo square plus, well, vector square plus V of A, no? This is my potential energy, my total energy. Then we said that given that the initial conditions are homogeneous except for this small inhomogeneities, I can neglect this term. And okay, and then I can plug my solution inside this kinetic this energy, and I don't have to do any calculation to convince you that this is given by a naught square times m square times r of t star. Okay, let me call it, okay, r star divided by r of t cube. Okay, where this a naught, so where they approximated that this a of t star is more or less a naught. So this a of t star more or less a naught. Okay, in principle, it's not clear that it really starts oscillating at T star. Maybe it doesn't start to be a cosine exactly at T star, but okay, it's a good approximation. To do it properly, you have to do it numerically, and here there's an order one factor. So here there's actually an order one factor between a naught and T star. So there's order one. Okay, that you have to do by computing numerically. So the energy density is given by this, is given by initial value of the field, mass field square, times a redshift factor, that's basically, sorry, here, well, to the fourth, to cube, of course, because, okay, the idea is that this a dot gives you a sine square, and then V of A gives you a cosine square, and then they sum with each other, and they give you 1, and that's why you don't have any more sines and cosine here. Okay, that's the reason. And this one you neglected. So this is the energy density. It goes down like 1 over scale factor cube. And the number density, corresponding number density, is rho A divided by the mass, and also goes down like scale factor cube. Okay, in particular, is something like a half a0 square times ma. Okay, r star. I call it as r star divided by r cube. It goes like 1 over r cube. So what we discovered is that by just having this particle there, at the time t star, its energy density starts going down like the scale factor cube, meaning that this energy density behaves exactly as cold dark matter. And indeed, you can interpret these axion particles as a bunch of particles at rest, these axion fields as a bunch of particles at rest when they're produced. And particles at rest, they remain there in the meantime. The universe expands, and okay, more universe comes. Okay, and the particles go far from each other in physical coordinates. Okay, and in the end, the corresponding number density decreases like scale factor cube. Okay, one comment. So first of all, this fact is correct. I'm not going to show it, but it's correct. The fact that the number density is proportional to 1 over r cube is correct. Also, if you assume that the mass is temperature dependent. In particular, if it turns out that the Na defined as rho A divided by Ma, where this average means average over a period of oscillation, this is correct. This also goes like r cube if alpha is different, alpha is larger than 0, let's say. So also in the case, the comoving number density is conserved. So also for the case of QCD axion is true. And also let me mention that in the case of the QCD axion, where this temperature, the temperature the temperature dependence, let me mention that as you see, at some point, okay, the Ma will converge to its zero temperature value, and at the time T star, no, Ma, so Ma of T star, no, is smaller than the final value, no. So there's a factor. There's a factor between the two. Okay, so it's smaller just because. Okay, you can see from this plot. So now the question is, first of all, okay, these particles, the shift as cold dark matter, but the momentum? Well, the momentum is more or less by construction 0, because I didn't put any special gradients in the field. Correspondingly, there's no momentum. In principle, there's more momentum coming from these fluctuations, but okay, for all practical purposes, these particles are very, very cold. So the typical momentum over their mass at the time T star is practically 0. As a result, these particles are super, super cold, and are much colder, at least much colder than, for example, WIMPs from thermal freeze-out. So these are extremely good candidates for cold dark matter, because they are very small momentum, and the shift has cold dark matter. So how do the redshift instead for what's the dependence on the energy density before this? Before this star? Can anybody tell me? The dependence, how does the energy depend on time? Energy density depend on time before T star? Yes. So means that the axion before that is a component of the cosmological constant, like of the energy of the dark energy. So here we have that dark energy, and here becomes like is my like matter. Okay. Yes. Yes. So first of all, the interaction with photons is a derivative. So the idea is that there's no interaction with photons, because you always have something like the mu a, and then you have some derivative of the current of some current, because the photon interact with the photon, you can always write that as a total derivative. No, so if the axion is homogeneous, there's nothing going on, like at least spatially. That one is not a total derivative, because you cannot well, it's actually the photon one is actually a total derivative. The gluon no. But okay. Yeah, I'm neglecting. I think there was some discussion at some point in the literature what is the effect of the thermalization of these axions from the. But I think this should be more or less correct. No, yeah. So I just wanted to tell you what we need to do now is to compute the corresponding energy density. Okay, we already computed it. No, just we don't know what is it in numbers, but in principle we want to actually get the correct number. To that, I have to do this unfortunate thing of having to calculate what is this T star. Okay, and and I don't want to bother you too much with these technicalities. But the idea is that to calculate this T star, you have okay, it's sort of very easy to do, but maybe a bit technical, okay, or boring. So I have MA at T star is defined to be basically Hubble at T star, no? Okay, then you remember this MA is given by lambda square over the phi, and then I have something like a temperature over, lambda over temperature star to the alpha over 2. Now this will be my MA of T star. This was in the increase there. Then I have to equate to Hubble, which is my order 1 conventions in something like T star squared over M Planck. So this basically gives me a formula for this temperature T star. Okay, so I'm just using the definition, and my formula for temperature T star is something like lambda, and then I have M Planck over the phi to the 2 divided by alpha plus 4. Okay. Okay, so basically T star is over the lambda if Fa were M Planck, but Fa is not M Planck. Fa is a bit smaller. So if I take Fa over the, let's say, 10 to the 9 GeV, just because just to see what happens. And okay, lambda, I take 150 MeV, and alpha, I take 8. Then this T star is something like 1 to 2 GeV. Okay. Of course, here there's also some number of degrees of freedom that I'm completely neglecting because I don't want to keep track of this stuff. But okay, the idea is that we are in a regime where we are in a self-consistent regime, no? Because we are in a regime where this T star is larger than lambda QCD, and so we can use this. Okay, the fact that the temperature went down exactly, so the mass went down exactly at temperature larger than lambda QCD, this the critical temperature QCD. So we are in the correct regime. Okay. Okay, and so we found that at time T star, the axion starts oscillating homogeneously. It corresponds to a bunch of particles that are basically free, and they basically redshift like matter, and they have a very small momentum. So now, computed this T star. Let me plug it back to the equation for the energy density. And if I do that, what do I get? Well, it depends whether if I'm talking about the QCD axion. I'm thinking what to delete. Or maybe I need a lot more space. It depends if I'm talking about the QCD axion or talking about an alp, meaning that if alpha equal to 0 or alpha equal to 8 or whatever. So let me consider both cases. Of course, QCD axions are a bit more motivated. So for the axion, what I want to do now is calculate omega A misalignment. No. Okay, for the axion, let's say QCD axion, this would depend on if you want A0 and on FA, which are basically my only two parameters. Okay, A0, I can also rewrite it like in terms of this. It is an A as a function of theta 0, because okay, theta 0 is like A0 theta 0 times FA. For the alp, I have a bit more freedom because I have this A0, which I still write in terms of 0, and then I have FA, and I also have MA, because in general the relation between the two is free. Okay. So I want to calculate this design abundance as a function of, for the QCD axion, these two parameters, and for the alp of these three parameters. When it's not that hard. So to do it, I do like this. So omega A misalignment is given by what? Well, it's given. Okay, this will be the energy density today, no? Given by this misalignment mechanism compared to the critical energy density. This is today, no? So let me put 0. Okay, let me put T0. So the critical density, this critical energy density, I can rewrite in terms of well, basically the energy density in photons today. I can write like as rho gamma or divided by omega gamma. Okay, so this is my easiest way to reproduce this to calculate this energy density. So rho gamma, you may know that is something like T gamma to the fourth. So these are the energy density in the CMB photons today. Okay, as is around. Okay, maybe there's a pi square over 30, and then there's a 2 in front. But for me, this is 1. This one I will forget. And this T gamma is around, let's say, 2 10 to the minus 4 eV. This will be the 2 point something Kelvin, famous. Well, this omega gamma is famously 2 10 to the minus 5. Okay, so instead of plugging the number of the energy density, I use these two numbers. Okay, in principle, I just plug a number of the energy density. Okay, and then what do I do for this log misalignment of T0? Well, I can take that one at the time T star and just do the blind thing of right shifting with the scale factors. So for that one, what do I do? Well, okay, first of all, I write this like, okay, let me do one more step. So this one I can do very roughly. Okay, I put equal even if it's approximate. This one is omega gamma from this. Then I have rho gamma, which is basically temperature of gamma to the fourth. Okay. Then omega misalignment, I write like MA 0, okay, which I just write like MA without okay, MA today. And then this will be the energy density in a misalignment today, okay. And a misalignment today, I can rewrite now in terms of that one. So this will be an A misalignment at T star, no, times the ratio of scale factors cube, no? And this will be R of T star divided by R T0. And conventionally, this R T0 is 1, and then I have a cube, of course. Okay? No questions? Yes. Yes. Yeah, ALP, so for the ALP, for me, ALP with temperature independent mass. So for the ALP, I have a mass that doesn't depend at all on temperature. In principle, you can start playing games with a mass that depends on temperature. So in a basically uncontrolled way, you can just say, okay, from a center temperature of maybe the confinement scale of the new sector, the mass starts decreasing for temperature higher than that, and then you're free. But for me, for now, I just take temperature dependent mass because I don't want to go into the complication. If you do temperature dependent, then you get different result. Other questions? No other questions. So, what is the ratio of scale factors in terms of the temperatures of the photons? How can I write this in terms of conservation of entropy density? Well, I deleted it, so you cannot check, but anybody knows. So you remember the scale factor was proportional to the more or less inverse of the temperature modulo the number of degrees of freedom. So in principle, I can trade this ratio of scale factors also with the ratio of the temperatures corresponding to T star and to T0, where basically the temperature of T star is the T star I wrote there, this one, given by that formula, and T0 is the temperature of the photons today, which is the T gamma. Okay, so now what I do is substitute this ratio of R with the ratio of temperatures. So this becomes T gamma cube divided by T star cube. Okay, this because of conservation of entropy. Well, and then then we're almost done, no? Because many things actually cancel with each other. This is the hardest calculation we will do. So, but it's important because it gives me basically the dark matter abundance for one of most motivated particles. So I guess we should do it. So this T gamma cube kind of cancels partially with this T gamma to the fourth. And so the result is like omega gamma MA over T gamma. Then I have my 1/2 M star, this is MA of T star, then I have A0 square, and then I have T star cube. Okay, where I substituted this NA misalignment with the formula there. Okay. Well, this would be an name misalignment at T star. Okay, the name misalignment at T star is substituted with the formula where I use this A0. Okay, this is the formula I wrote there. And also, notice I put T star instead of putting MA because I told you that the number density is conserved from this time T star on. So from this time T star, the number density is conserved. So so this M star will be MA let me write it explicitly, MA at T star, A0 square. Okay, so long story short, I get this formula, and then this T star I can rewrite this in terms of the Hubble parameter and then Planck, because I'm a denomination, so I have this formula for T star. It's basically Friedman equations. And the calculation is done. So this H star, well, I can this is also M star, no? This is MA of T star. Okay, and I just start plugging in the numbers, and I get the formulas, the following beautiful formula for the dark matter abundance, which is omega A misalignment equal to, well, I have theta 0 square, which comes from this A0 that I write like theta 0 times FA. Then I have, well, I have FA over M Planck square. Okay, let me write it, then I tell you. Then I have MA over 4 T gamma, okay, square over M Planck. These are okay, and I have omega gamma to minus 2. Okay, and this is the 1/2. Okay, and then I have MA divided MA at T star. Okay, to the 1/2. Okay, so this is the same formula as here. This is the same exact formula. Just I wrote like M Planck. I wrote in this way. Okay, and T gamma. Okay, I wrote like T gamma squared to the 1/2. Okay, just because. And okay, and also divided by MA to the 2.5. So this is the same formula. You can check this exactly the same formula. But why did I write it like this? Because 2.5. Yes. Okay, you can just, this is a mathematical identity you can check. Why did I write it like this? Well, because you see that this we know that observationally is 0.25, no? This 0.25 observationally. And this number here is the temperature of the photon square, which is something like 10 minus 4 eV, then over M Planck. So and then this gives me a factor of 10 to the 10. This because it's omega gamma to minus 2 gives me 10 to the 10. So in the end, this result this gives me something like 10 to the minus 25 eV. So it means that if MA is over 10 to the minus 25 eV and FA is over than Planck, then I get the correct dark matter abundance for theta 0 over the 1. In other words, these are more or less an analytic formula. Okay, I didn't plug any numbers, but more or less it tells me that if my initial displacement is over the M Planck, maybe a bit below, and the mass is around 10 to minus 20 eV, let's say, then this axiom gives me the correct dark matter abundance. Here, I'm assuming that MA is equal to MA of T star, so this factor cancels because I am okay. This works for an ALP. So for an ALP, if you want if I put alpha equal to 0, meaning an ALP, I get that MA omega A. If I actually plug the actual numbers, is like misalignment is something like 0.1 theta 0 square. Okay, this is the same formula, but written in terms of number, FA 10 to the 17 GV square. And then I have MA 10 to minus 22 EV. Okay, this is the actual formula where this factor cancels because I put alpha equal to 0. And this is a miracle now because nobody asked that. Okay, for FA and MA reasonable values, you will get the correct dark matter abundance, but indeed it is the case. For let's say FA over the Planck and MA over 10 to minus 22, you get the most correct dark matter abundance. And here I have to say something else. So first of all, there's a strong dependence on FA and a weaker dependence on MA. So basically, by changing MA by order 10 to the 10, it doesn't change too much because there is only a weak dependence to the 1/2. while FA changes the dark matter balance a lot. So basically, you can reproduce the dark matter balance for basically all values of MA. Then we will see later what are the actual values for FA or M Planck or just below. Of course, if you increase MA, you need to decrease a bit FA. Okay, and then you get. And also, let me tell you that there's a strong dependence on theta zero, so which is in principle an unknown parameter that depends on the cosmography of our universe. Okay. Then, okay, let me also give you some intuition why there's the dependence on FA and MA. So FA comes from the fact that the initial energy density was, remember, was MA square, A0 square, no? Which is basically FA square times theta zero square, okay? This was initial energy density, and this basically implies this dependence on FA, okay? This dependence on FA square. But why there's a dependence on MA to the 1/2? Well, because despite the fact that there was a dependence on MA square in the initial density, well, I also have this redshift factor that depends on MA itself. Now, this redshift factor here depends on MA secretly inside T star. So if you want, the lower is MA, the higher is MA, the more time you have to, these particles behave like dark matter, the more is the time that these particles behave like dark matter. So I get more redshift, and this basically decreases the dependence on MA from power 2 to power 1/2. So the power 2 to power 1/2 comes from the fact that for higher masses, I have more redshift, okay, because this time T star is earlier in time. Okay, so this is just a final result, and that's it. This is for an ALP. I wouldn't call it's not really like a miracle because here I put some information. Of course, I put some information for new physics that are non-trivial. While for the WIMP, okay, it's a bit more automatic, but it's still a nice fact. And then let me rewrite this formula also for the QCD axion. So for alpha equal to 8 QCD axion. So I'm not gonna derive this, but okay, you just obtain via the same formulas. Okay, you have to plug this ratio of masses, where this MA of T star now is obtained by the formula I told you before. So if you want, okay, maybe I'll do one more step, just not to. So MA, I do MA of T star. Okay, MA of 0 divided MA of T star is equal to, well, something like lambda square over the Φ. This will be MA of 0, and then I have T star over M Planck. Okay. Then if you plug in the formulas I gave you before, this is basically M Planck. This formula for T star is M Planck over the Φ to the alpha divided by alpha plus 2 alpha plus 4. Okay, whatever. Okay, if you plug this dependence here, so you see that this factor is clearly larger than 1. Okay, basically.
You mean the M Planck over Φ?
Yeah, M Planck.
The power is 1/3, right?
Yeah, this is M Planck over Φ. So alpha by alpha plus 2. Yeah, this factor is larger than 1. Yeah, all this stuff is larger than 1, which means basically, as I told you before, this means that the MA at T star is smaller than MA. So because you have these two cross when the axion mass is still increasing, so the axion mass final value is larger compared to the axion mass when they cross. Okay, except for this stuff. So if you plug this in, you get this formula, and MA misalignment for the QCD axion, which is very simply 0.25, which is the observed, okay, times theta 0 square times Fa over 10 to the 12 GV to the 7 over 6, and then 7 over 6. And then there are also some factors that depend on number of degrees of freedom that I've just put to 1. So these are invisible factors that depend on number of degrees of freedom, but forget about them. So long story short, so to obtain this formula, I also use the fact that for the QCD axion, the mass I use the relation between a mass, MA, and FA for the QCD axiom that I wrote last time. No, you can also, you have to put the relation between the mass and FA for the QCD axiom. Okay. For QCD axiom, I get the correct quantum abundance for FA around 10 to the 12 GeV for theta 0 over the 1. So, and this FA, as I told you last time, is not ruled out by, for instance, absolute observation. And this is the final result. So QCD axiom can be a dark matter via this simple mechanism for, in principle, a large value of values of FA. And now let me, okay, and then this Bennett 7/6 comes from the combination of this that FA squared, that MA to the 1/2, and that MA over M star to the 1/2. Okay. And here I wrote for you this MA over M star to the 1/2, so you can check that that's the case. Basically, it comes from the 2 plus 1/2 minus 2 minus 1/2 minus the other things. So a few comments, except for like it's a miracle, even if it's a bit less of a miracle than the WIMP. The first comment is the fact that theta 0 is in fact undetermined. So we don't know what is theta 0. As I told you, theta 0 depends on the cosmography. So in some patches of our multiverse, the theta 0 can be large. Some other patches can be small. And we have, in principle, no way to tell what theta 0 has chosen in our universe. So here I'm showing famous plot where I have my axion distribution. There will be some patches, no, where theta 0 is large, some patches where theta 0 is small. And for these patches where it's smaller, the dark matter abundance will be underproduced for a fixed FA, or will be produced less. Those with large theta 0 will have larger abundances. And this is a cosmographical property of our multiverse. Okay, and fine-tuning theta 0 very close to 0 is not actually a fine-tuning of a Lagrangian parameter, as it was for the strong field problem, because theta 0 is in principle a cosmographical property, and you don't have a prior of how to distribute this theta 0 over the multiverse. Okay, this is just a comment. So in principle, if I fix FA, set 10 to 12, the patches where is over the 1, I get correct the quantum abundance. For those where if theta 0 less than 1, I get another abundance. And maybe you can even use some anthropic arguments to, this anthropic argument that you claim that indeed we were in this patch, because otherwise there wouldn't be enough dark matter. Okay, this is just a comment. So one, ALP might be a nightmare scenario. No, it might be a nightmare because I gave you the formula there, and the formula tells you that even if I have a scalar field that is uncoupled to the standard model completely, that with very small mass, then I get a correct quantum abundance, and I have no way to test this thing because it can be completely uncoupled to decoupled from the standard model, and it would be a complete nightmare for us because we couldn't know what is the dark matter because we could not measure directly except for gravitational interaction. But if the mass is large, axial mass is large enough, this gravitational interaction will look like basically a normal cold dark matter. So this doesn't make us happy. On the other hand, we are a bit happier because of the fact that among these ALPs, the QCD axiom maybe is more motivated, and we know for the QCD axiom there's a coupling to the standard model. So QCD axiom makes us happier. I mean, at least me. Then I know you, but so as a consequence, another consequence is that as soon as I put a scalar field with small mass in my Lagrangian, I get that quantum abundance. So if you want, unless this field cannot decays in some way, this field will always give me some contribution either to all the dark matter or to a subcomponent of all the dark matter. Okay, and this might be relevant, of course. And also, this production mechanism is completely non-thermal, meaning that okay, I never use the fact that these particles were in thermal equilibrium with the standard model, where it's completely visible decoupled scalar field to the thermal bath. Okay, and if you want, okay, let's say FA, if you really believe in naturalness, even cosmographical naturalness, then if you put theta 0 over the 1, then FA 10 to 12 will be more motivated, and maybe So, and this corresponds to MA, let's say 6 10 to the minus 6 eV. So if you really believe in cosmographical naturalness, okay, but that's not necessary. So what happens if I start increasing theta naught? So theta naught, I told you, is between minus pi and pi, but what happens if I start pushing theta naught close to pi? Nobody. Yes, but not only. So if I start pushing theta naught close to pi, I start probing. So remember, I have this potential, and I approximated the quadratic. The action has a quadratic potential. If I start choosing theta naught close to pi, then I will also need to include the nonlinearities of the action potential, which I will not do, of course, because there is no time. But the idea is that as soon as the more you go close to pi, the later the action oscillates because of continuity. So if theta 0 is exactly pi, then it doesn't move. If it's pi minus epsilon, then it moves, okay, it's pi minus epsilon, then it moves later and later in terms of cosmic time. However, it moves cosmologically later. And, okay, in that case, the abundance is increased with respect to this formula here. In particular, okay, let me write it here. Okay, now I kind of deleted the important thing, but okay, let me put it for the use of the axiom. In fact, if you start putting the theta 0 close to pi, this formula gets corrected with a function f of theta 0. Okay, this f of theta 0 is 1 when theta is close to 1, and then it's non-zero close to pi. And okay, long story short, you can calculate this f of theta 0 is something like log to the gamma, okay, log to the gamma of, let's say, 1 over pi minus theta 0. Okay, so this is actually a fit of you have to solve it numerically because it's not that you can solve it numerically. But the idea is that as soon as you start, you're close to pi. In reality, the action kind of goes. The field starts rolling very fast from the maximum, and therefore, basically, the time when it starts oscillating, let me call it T star again. Okay, or T osc means the time it oscillates, goes like some power of the log of this log. And this is why this dependence here. Okay. So you increase the dark matter abundance, but you don't increase the dark matter abundance power-like, but only logarithmically. Okay. But what happens if this start? So they're clearly bounds now because I cannot go arbitrarily close to pi. First of all, because the action needs to be the dark matter. If the action starts oscillating after matter relation equality, cannot be the dark matter. So that's a very trivial bound that I can put on how much close to pi I can be. Okay, that's the first bound. And this, if I remember well, but maybe don't take me for this. I think if you start around theta minus, okay, something that looks like a fine tuning. If you start like theta 0 over the pi minus something like 10 to the minus 6, which is basically very close to pi, then it starts oscillating after matter relation equality. Or here, okay, don't take this. There's a big number, but okay, don't take this number exactly. But there is actually a larger bound, a stronger bound that comes from this. That comes from for this scenario. Okay, so I don't want to give you too much detail on this bound, but this is sort of interesting because it's related to the initial fluctuations of the universe. let me tell you that in the end, the abundance will not be the same exactly in all the places in our universe because of the initial axion isocurvature fluctuations. Okay, you remember that initially I told you. So let me now discuss very quickly the isocurvature bounds. So initially I told you that the axion is gets increased exponential during inflation. All the fluctuations get smoothed out, but inflation in the meantime it gave me some initial fluctuations of the axion field. These are isocurvature fluctuations, and these are problematic. Okay, this corresponds to the fact that consider, for instance, the universe at the time of decoupling of the CMB photons. The universe has a size, moving size of all the, let's say, 0.01 or 0.05 inverse megaparsec. Okay, it would be the one over this. Okay, this will be the typical size of the universe. Okay, it's a macroscopic scale. This is as curvature fluctuations. What do? They assign to me a value of theta that is a bit different in different patches of my universe. Okay, at this epsilon. Okay, let me call it epsilon tilde. Is not the same epsilon in our big universe. So these fluctuations are small, but they're still there. And we know observationally that the dark matter cannot be different. So the different patches will give me different dark matter abundances. No, because here the dark matter abundance will give me will given by this formula with this theta 0 plus epsilon, and this other patch I get another dark matter abundance with theta 0 with a different epsilon. You say epsilon is very small. Who cares? True. But we actually have very good cosmological observations of the amount of dark matter that can be, or amount of isocurvature fluctuations of the dark matter at cosmological scales. Okay, so this is a problem. So the fact that there's different dark matter analysis means that yes. Who told you this? You knew? Sorry? No, so true, but there's this fact that during inflation, all the scalar fields get these curvature fluctuations. Okay, so with the light scalar fields get these curvature fluctuations. So the field is as the same theta 0, no? The field has the same theta 0 because of the inflation, but in basically at all length scales, on top of this of this constant value, also it gets fluctuations that are very small. Indeed, this epsilon tilde is of order of h inflation over 2 pi. Okay, over 2 pi fa. No, this will be corresponding fluctuation of theta. No. And as I told you, these are problematic, you know. In fact, if you look at the universe, it's not like you look at one direction, you see, you know, dark matter much different, a density much different compared to the opposite direction. You say more or less the same value. Okay, the value is in accordance with what we call adiabatic fluctuations, and the difference compared to the adiabatic perturbations is constrained. Okay, so let me tell you that. Okay, in formulas, this means that delta rho over rho in these different patches, because of these isocurvature fluctuations, is constrained to be something like delta rho over rho, or because of the adiabatic, times a factor, let's say 10 to minus 1 or 10 to minus 2, which means that, and these adiabatic fluctuations are the famous fluctuations, can be related to the famous fluctuations on the photon temperatures, which are famously of the order 10 to minus 5. So long story short, these are cosmological bound. And we need to impose that if I look at a patch of cosmological size over time of materialization equality and another patch, then these two patches give me an abundance that is less than 10 to the minus 6 in relative difference. Okay. This is a long story short. Because the amount of curvature fluctuations is bounded to be basically 10% than the adiabatic ones. And this basically gives me a bound on the Hubble schedule inflation, because I don't want to delete important things, so let me delete this one. No, because the idea is that this delta rho over rho you can relate to theta zero, okay, and to the Hubble schedule. So this delta rho over rho, what is that? Like, okay, I'm not going to do all the details, but the delta rho over rho is given by the delta rho over delta theta. No, then with this delta theta, okay, delta rho over rho over delta theta is basically from that formula there. Use some derivatives which I'm not going to do now. That formula there. While delta theta over is, as I said, hi over 2 pi fa. Okay. Okay, and this I have to impose that this is less than 10 to the minus 6, more or less. Okay. This one over. Sorry. So I'm not actually gonna go to the calculation, but the idea is that if you put this, okay, here put the 0 just to be consistent. If you plug this formula here with this f, okay, you can do it. Plug this formula with this f, and impose less than 10 to the minus 6. Then I get a bound on the Hubble schedule inflation. So Hubble schedule inflation actually you have to do it numerically because there's a log going on there. I get that is more than something. On the other hand, Hubble inflation cannot be too small. And okay, because basically, because Hubble inflation is expected to be a macroscopic scale, let's say, over the 1 eV. Okay, because it's related to maybe to the heating temperature. So Hubble inflation cannot be too small because you have to allow, biogenesis and so on. And this basically implies, okay, if in that in this, so imposing that Hubble inflation is on the other end larger than about 1 eV, no? This gives me, this implies that, okay, for theta 0 minus pi much more than 1, this gives me a Fa larger than 4 times 10 to the 9, okay, 10 to the 9 GeV. So this gives me a bound on the maximum amount of tuning I can do, tuning, cosmological tuning that I can do around theta 0, around pi. Because if I do too much tuning, then these patches will start oscillating too late, and they will create too much different dark matter abundance. And this gives me a bound on theta 0, which I can translate on a bound on Fa. Okay. So in the end, what do we get? So we get a lower bound. So for the correct dark matter abundance in this scenario, I get that Fa can be around, let's say, 4 10 to the 9 GeV because of this isocurvature fluctuation story. Okay, this one cannot be relaxed too much. You can only relax if you decrease this Hubble during inflation. Okay, but only depends on logarithmically in the end on the bound depends on Hubble during inflation, and then it will be smaller than let's say m Planck, which is 10 to 18 GeV. So this is my expectation in this scenario. So this is a theoretical prejudice. Okay, this fact that I cannot go above m Planck, and this comes from isocurvature fluctuations, ISO, and this is cannot go above m Planck. Okay, and okay, the theta 0 here corresponding to theta 0 here is much more than 1, so it's like 10 to the minus 5 or 6, no? And here is very close to pi. Theta 0 is pi minus epsilon. So indeed, if you put theta 0 very small, you can get a large abundance with larger Fa. No. So in the end, and this corresponds to an axiom mass, if you want, between uh, 10 to the, okay, 10 to the 18 corresponds to maybe 10 to minus 12 EV. Okay, this is a very rough. Sorry? One line? Yeah, so the equality are a bit messed up. Uh, but okay, this in the range, and this corresponds to maybe 10 to minus 3 EV, something like that. So long story short, in my multiverse, I can get the correct Diagrammatic abundance basically for all the values of MA in this range by choosing the the correct value of theta 0. So if theta 0 is very close to pi, I can get the correct Diagrammatic abundance for a Fay around 10 to the 9, 4 10 to the 9 GV corresponding to this axiom mass. And if I can tune theta 0, so if theta 0 is very, very close to 0, then I can get the Diagrammatic abundance for large values of a Fay. And this, and the final story is that I can put this in the famous Ga gamma gamma plot and see what what I get. So in the end, the final result would be that if I put it in my famous plot with Ga gamma gamma versus MA. So here I have something like 10 to minus 11 maybe. So divide GV to minus 1. And here I have 10 to minus 20. Okay, maybe 17. Okay, these numbers, you have to take them with some grain of salt. 10 to minus 22 EV. And here 10 to minus 11. And here 10 to minus 3. Okay, the QCD axiom I wrote, okay, maybe 10 to minus 12. The QCD axiom will be somewhere here. And here you have this your KSVZ model and the DFSZ model. So, and these bounds, again, they come from the fact that I cannot go for FA larger than Planck, and here I'm bounded by isocurvature fluctuations. And I can get the correct Diagrammatic abundance for all these values. So, of course, if you go down, you have a smaller access to photocoupling, okay, and you know. But all these values are implicitly motivated radically. Those that are close by here, maybe they correspond to more motivated in terms of having theta 0 over the 1, but that we don't know. And then for the ALP, there is for the ALP, in fact, two parameters, so I can just write G gamma gamma equal to alpha electromagnetic over 2 pi Fa. Okay, if I do that for the ALP, in principle, I get contours like this because I can choose it. So this contours correspond to theta equal to pi minus epsilon. This corresponds to theta equal to 1, and this corresponds to theta equal to minus pi. Okay, and you cannot go up too much small masses. Okay, maybe this is the opposite pi minus epsilon. This is 1, and so on. Yes, more or less like this. Okay, and basically you can produce the Diagrammatic abundance below here, and you can go above because otherwise, you have this isocurvature fluctuation bound. Okay, so basically you should look at the axiom more or less everywhere, because okay, except for this here, is to populate also this parameter space. But in principle, the axiom is very motivated for all the values of the masses. And the ALP basically for all the values of the masses and even of G gamma gamma, except for maybe too large. This is basically a theoretical prejudice, but it's not really like okay. This basically what the theoretical calculation gives you, and then of course once you detect something, you have to interpret it theoretically. Questions? Yeah, that's the next topic. In the next 10 minutes, I will tell you what happens. What? No. This is okay. This is okay. Since you mentioned this is the pre-inflationary scenario. It's called pre-inflationary. Pre-inflationary. Okay. Then and now I'll tell you what happens for the post-inflationary. So I repeat that this bound here comes from isocurvature fluctuations, and this one comes from the asking that the phi is smaller than is larger than smaller than Planck. Close to here, in fact, you have other bounds coming from something called superradiance that I'm not going to talk about. Okay, but here there are actually other bounds because you see the axiom. So maybe exactly at this point you don't want to be, but okay, here it's fine. Okay, then you have the famous bounds from several experiments that look like this. These are bounds from actual bounds from actual measurements. Okay, so for now, I talked about what happens to a constant axion, a homogeneous axion field, but I cheated, in fact, because this is not always the case. All this discussion assumes that the following thing. So here I cheated because I assume that the temperature of the universe, let me delete this thing, the temperature of the universe was always smaller than Fa. Temperature of the universe was always smaller than Fa. And, or more precisely, the scale of symmetry breaking of the Pechet-Quinn symmetry, okay, like we call it V last time, and Hubble during inflation is also smaller than Fa. So if you want, it corresponds to low-scale inflation, not high-scale inflation, low-scale inflation. This is the temperature of the universe, specifically is the temperature of the heating after inflation, or the maximum temperature, okay, maximum temperature after inflation, of the universe after inflation. What happens if it's not the case? So suppose that instead, so this, I assume this, what happens if instead the temperature of the universe was larger than Fa, or V, okay, let's say V. This, well, in that case, at some point during my universe, I cannot treat the axion anymore as a correct degrees of freedom, no? Because as you might know, finite temperature corrections to the Pechet-Quinn potential become important. So remember yesterday we discussed a model where I had axion field embedded in a compact scalar field, called the KSVZ model, where the axion was the phase. Okay, this is the axion. So, and this Pechet-Quinn field has some sort of Mexican potential like this. Okay, this will be V of phi. And the axion was this angular variable. Okay, so in reality, what happens is that at very high temperatures, in particular temperatures larger than the typical scale of the typical VEV, so temperature larger than typical VEV, which we remember it was NFA, but okay. Temperature larger than typical VEV. What happens is that these particles, the particles phi, if they couple to the standard model as they should, because the axion is coupled to standard model, or anyway, the gluons, so the quarks, the hidden quarks are coupled to the standard model. No, then this phi gets a temperature correction, and instead at high temperatures becomes like this. So instead of being a Mexican hat, becomes a paraboloid. And this is a very known fact, kind of known fact of thermal field theory. And you can think of this as having an effective mass term that is of the order of the coupling square to the thermal bath times the temperature of the thermal bath times phi square. Okay. And you can think of this as these particles being this thermal bath, but then scattering with the thermal particle bath and acquire an effective mass just because they go slower. No? This is the intuitive way to see this correction of the potential. They go fast, they interact with the thermal bath at high temperatures, and they get an effective mass. Okay, so in reality, we say that at high temperatures, the Pechet-Quinn symmetry is restored. Symmetry is restored. So at high temperature, Pechet-Quinn symmetry could have been restored. So what happens as the universe goes through the so-called Peche-Quinn phase transition? Well, the potential changes from a parabola to a paraboloid to a Maxian hat. And during this period, the corresponding scalar field gets big fluctuations. So, okay, so let me tell you more in detail. So at high temperatures, the correct degrees of freedom are not anymore the axion and the radial mode, but rather than the real and imaginary parts of this complex scalar field, no? Because you know, if I have temperature much larger than V, no, which is a Fa, whatever, then the potential is a paraboloid. Now, if I minimize down the minimum is 0. So the correct degree of freedom are the real imaginary part. Okay, no, it's not that important. So the axion doesn't exist. Only the real imaginary part exists as propagating the degree of freedom. So what happens? So initially, the potential looks like this, and then it becomes like that. So you can imagine the imaginary parts have small fluctuations. They are sort of waves that have small fluctuations around in every point around the minimum. But then there's a phase transition that happens. When a phase transition happens, different patches in space, no, will correspond to the angular mode of this potential, which is the axion, rolling down in different directions. So, for instance, in this patch, the axion is created, but is created at this value, for instance, a equal to 0, for instance, corresponding, let's say, to theta equal to 0. Theta 0 equal to 0. This corresponds in one patch. Then in another patch, it can be like theta 0 equal to 1, theta 0 equal to 2, and so on, theta 0 equal to 1.2, and so on. So this basically is called the keyboard mechanism, and this tells you that after phase transition, the field goes to the minimum, but even if there's a U1 symmetry, you don't know what minimum to choose. So different patches that are causally disconnected will go to different minima because basically they don't know. They don't know which minimum to pick because they're causally disconnected. Okay, and let me tell you that similar things also happen when the Hubble inflation is larger than V. Because in that case, what happens is these fluctuations of the field of the angular field come along because the field itself fluctuates a lot during inflation. In particular, it fluctuates so much that it fluctuates in space, so much that it gets inhomogeneities on scales that are actually avoided h inflation to the -1. So in this case, you get inhomogeneities of scale R that are h inflation -1. So in both cases, long story short, you're in a very different scenario with respect to what I told you before, no? Because before we had a homogeneous axion field, and here you have a field which is completely inhomogeneous on small scales. So here corresponds to h inflation -1, which is a very small scale in terms of cosmological scales. And here you get inhomogeneities on scales that are of order of the inverse temperature, and maybe is of order of Fa. So in this case are of order of Fa. So these are macroscopic scales, no? So they're very small scales. Fa is super small scale, like smaller than the proton size. So in this case, so if the temperature, so if you want the maximum, okay, the minimum, or okay, if the temperature or the heating is larger than V and or the Hubble inflation is larger than V, then you are not in the pre-inflationary scenario. In particular, we say that in this case, we quote-unquote restore the Peche-Quinn symmetry after inflation. So the symmetry is restored. Okay, and then after the transition, it's broken again. So this is called post-inflationary scenario. This is called the axion post-inflationary scenario. And in this case, contrary to the previous one, the axion has inhomogeneities in the initial conditions. And these inhomogeneities are extremely problematic because they render the equations of motion nonlinear. So it's impossible. Okay, I'm not going to write the I just want to say that this is called post-inflationary, just because the paycheck equilibrium is broken after inflation, post-inflationary. Okay, and the axion is inhomogeneous. Homogeneous. Okay, so what do you think I should change compared to the previous derivation if the axis is inhomogeneous? Yeah, so I neglected, before I neglected the derivatives, no? So I did something like this, a dot dot plus 3h a dot minus Laplacian of a over r squared plus v prime of a equal to 0. And then I threw away this stuff because I said the derivative was not important. Okay, let me just put this one for now, like ma squared times a. Okay. On the other hand, now I have to consider also the special derivatives, and also the initial conditions will look like something crazy. It's not going to look like to be a field with some modes and so on. Maybe peaked with modes peaked maybe at this momentum scale corresponding to the temperature. However, you can still be a bit naive and try to solve this equation, because in principle, it's not everything is lost, no? Because if I have a field, so this equation is still linear, no? If I neglect the nonlinearity of the axion potential, this equation is still linear, no? This equation looks still like something like, okay, this is linear, okay, and even if I consider this term here. In particular, what I can do, I can go to momentum space, no, and okay, define the Fourier transform of AK, which I just call AK. No. This equation will tell me that AK dot dot plus 3H AK dot, no? Okay, plus K square over R square. Okay, and then I have maybe plus MA square A equal to, so this is AK. No, I'm just taking the same equation. I just wrote going to Fourier space. The Laplacian becomes a minus K. Okay, and here basically I'm solving the equation for each Fourier mode. This equation has in fact even an analytic solution. So it turns out that now I'm not going to write too much detail, but the idea is that I have my Hubble horizon H star at this time, no, this famous time T star, no, remember, which basically determines when this term is equal to this one. So, and initially you have some modes that are super, no, they're all scales now, but in principle very homogeneous inside this Hubble horizon, no. The idea is that if you solve this equation, all the modes, I'm done. All the modes that are smaller, that are larger than K star, this H star, no, all these modes like that. All these modes that are larger than K star. Then the decay. In fact, you can show that AK goes like 1 over R square from this equation. No, sorry, 1 over R. And the corresponding energy density at OK goes like 1 over R to the 4th. No? Because it's AK squared, and I have a dot. Okay, and then it gives me 1 over R to the 4th. So these modes that are inside the horizon, they decay. And they just give me, in the end, at the time T star, no? The field will look like homogeneous, no, on scales that are over this upper parameter. So if you want, the field looks like homogeneous here, then okay, homogeneous there. Okay, with this H star minus 1, because all the high momentum mode decay. On the other hand, the modes that are large with K, which is smaller than MA, they're frozen. They don't decay. You can see from this equation, they're equivalent to just neglecting this term compared to that. So those they don't decay. Those with AK, okay, K over R star smaller than MA star. So if you want, or this H star, they don't decay. They're frozen. But OK is frozen. 1 over R to the 0. So long story short, in the end, despite this fluctuation, in the end you expect that at the time t star, you still have a field that is more or less homogeneous at scales over the h star. And in this way, you can even do, okay, now we have a field that is homogeneous over the star, we can, of course, our horizon today will be much larger than this. So we'll enclose many of these Hubble patches. So in the end, what we have to do is take the average. Now, in the end, the field starts oscillating inside all these patches, like in the pre-inflation scenario. So inside these patches, I can take more or less a homogeneous approximation because all the other modes have decayed. And then I can take the average over all Hubble patches inside our Hubble patch, and I get a formula. And contrary to the previous one, this one is predictive, no? Because now you don't have to choose anymore the value of theta zero. All theta zeros are chosen, no? So for instance, this one will have theta zero equal to 1, this one theta zero equal to 2, and so 2.1, and so on. So this way I can do this average and get a unique prediction, no, for the value of Fa that corresponds to the dark matter abundance. And long story short, if you do that, turns out that, okay, I can just, what you have to do in practice is substitute in the previous equation I show you, theta zero you have to substitute with theta zero effective, which is around 2.15. Why is that? Well, because it's like taking the abundance I wrote before, theta A misalignment, which is a function of theta zero, and then I have to integrate in basically in the theta zero over to pi. So this idea, no, I have to integrate over theta zero. So this gives me something like, okay, in practice, what this boils down to is to do like this integral, which I'm okay, very simple. This, and then I have this also my function f of theta zero, which is also takes into account the non-linearities and stuff. And if you do this corresponds to an effective theta zero that is this 2.15. No, theta zero squared that is 2.15. Okay, this is the effect, which is this one. So and this one. Okay, this 2.15, I plug in my abundance equation and get my result for Fa. And I get Fa 10 to the what? Well, I don't know it because it's not relevant. It's around 10 to 11 or 10 to GV. The problem is that the stuff is actually much more complicated than this, and tomorrow we're going to talk about tomorrow. It's because, in fact, there are non-trivial configurations of the axion stream that are called axion streams of domain walls, and they contribute to the dark matter abundance, and they completely screw up this estimate. So this estimate is wrong, and that's why I didn't spend too much time on this. But yeah, so tomorrow we'll see that, in fact, the axion has non-trivial configuration that are called cosmic strings. So there are configurations where basically the long where basically there are lines where the axion wraps non-trivial between minus pi and pi around. This is a basic solution of the equation of motion that we will see tomorrow, and these configurations are formed after the phase transition. They evolve and they emit axion waves, axion dark matter, and they contribute to the dark matter abundance, and they change this prediction. So this prediction is wrong. And okay, and we will calculate tomorrow what is the abundance coming from the decay of these configurations. And okay, and then we will see that these configurations also lead to a non-trivial structure of the dark matter at small scales, because these patches correspond to overdensity of the dark matter at small scales that you can maybe detect. Okay, thank you. Yes. Well, that's all. Yeah. Well, now we start going to complicated stuff. So I can see neglect because in effect the derivative, morally, what I have to do is like I have dA over Fa, and then I have some currents, let's say. But this d mu A that is relevant. So A is maybe over the Fa, let's say, because A is theta zero Fa, so this is over the 1, let's say. But the derivative only is morally of order h star to the minus 1, because I told you that it's this case that are important. No, at late times in this case are important. But h star, okay, the mu is over h star. So the derivative, okay, the derivative is like 1 over equal to the momentum typically is this one, but the ratio between H star and FA is much more than 1, no? So H star over FA is basically MA star over FA, which is much more than 1, because, okay, MA is much more than FA, because, okay, it's basically lambda QCD over, okay, okay, some formulas. It's much, so in principle, if you only consider momenta that are order H star, this is not relevant. But if you consider very early momenta, so indeed what happens is that these initial waves, these initial fluctuations of order fade, those you have to consider the effect of the coupling with the photons. And this leads to some non-trivial effects like dragging of strings across like friction of strings across the thermal bath. So that's something more complicated. But at late times, in principle, it's negligible.